In this second lecture on Chapter 10, we are going to take a look at the different gas laws. There are multiple gas laws that we can look at to study the relationships between the different variables that affect gases. So we have pressure, volume, temperature, and then the number of moles of a gas. So we'll look at several laws that compare two variables. Then we'll move into our ideal gas law, which is going to consider all four variables, and the combined gas law, which covers three, or contains three. With all of these laws, I have a problem that I've worked out that I'll walk you through so that you understand how to recognize and solve for the different gas law variables. For a lot of you, this is going to be a review. You've probably studied about gas laws in a class before. So just kind of refresh your memory, use this as a memory refresher, and practice these problems as I go along. So our first gas law that we're going to look at is Boyle's law, and this describes the relationship between pressure and volume. And this is an inverse relationship, which means that as one goes up, the other goes down. So I have here, pressure going up, volume going down, pressure going down, volume going up. And what you'll see as we go through, as you read in the book, and also as we go through these notes, that we use this letter K to represent some constant value. It doesn't have a real value. It's an artificial value. But what it does is allows us to be able to compare two sets of variables. It allows us to be able to set up P1V1 equals P2V2. So it just allows the comparison, because P1V1 is equal to some constant value. P2V2 is also equal to some constant value. So we can set those equal together, or we can set those equal to one another to be able to work our problems. And as long as we have three variables, we can solve for the fourth. So when you're working these problems, you want to be able to look for and identify the three variables that you have and the one that you need to solve for. So here's our question. The volume of a gas is 20.4 liters when the pressure is 925 kilopascals. At constant temperature, a change in pressure causes the volume of the sample to change. If the new volume is 30.6 liters, what is the new pressure? Okay, so if we consider this problem, they've told us the volume of a particular gas when or at a certain pressure, and they've told us that we have constant temperature, so we know our temperature is not changing, but we do have a change in pressure that has caused the volume to change. So the new volume there is 30.6 liters, and we want to know the new pressure. So the volume here is 20.4 liters when the pressure is 925. So that's going to be our V1 and P1. 20.4 liters and 925 at 925 kilopascals. Then they tell us that our new volume is 30.6 liters. They want us to solve for our new pressure. So we set up P1V1 equals P2V2, and we know that we need to solve for the second pressure, so we are going to put that by itself in the equation. So that's why I've got P2 times 30.6 liters, and then I divide both sides by 30.6 liters. I'm left with when I solve, I get 616.6, which is going to be 617 in significant digits because I have 3 in my problem. And that's in kilopascals. Now, when you work Boyle's law problems, it does not matter what unit of volume or unit of pressure you use as long as they are the same. So both of my units of volume are liter. I've got a pressure unit of kilopascals, so my second pressure will be kilopascals. So it doesn't matter what the units are as long as they're the same. Now we need to figure out, does this answer make sense? So our volume increased, and since we know that this is an inverse relationship, if volume increases, then pressure has to decrease. And we see there that the pressure went from 925 to 617. So we see that the pressure did in fact decrease. So that is a Boyle's law problem. Now we get to Charles's law, which looks at temperature and volume. And this one you see is a direct relationship. So what happens to one happens to the other. So if temperature decreases, volume decreases. If temperature increases, volume increases. And just like before, we can set that equal to a constant. So this time, though, with that direct relationship, we say volume divided by temperature. So when we set up our equation, we're going to have V1 over T1 equals V2 over T2. Now this time, you see my note there, temperature must be in Kelvin. Volume, it doesn't matter. Typically it's going to be in liters, but it doesn't matter. But temperature must be in Kelvin when we look at Charles's law. So here is an example of a Charles's law problem. Calculate the decrease in temperature in Celsius when 2.0 liters at 21 degrees Celsius is compressed to 1.00 liter. So the first thing we need to do is convert our Celsius temperature to Kelvin. So we add 273 and we come up with 294 Kelvin. We're given V1, T1, and V2, so we're solving for T2. So when I set up my equation, I'm going to set it up so that I kind of cross multiply and I come up with V1 T2 equals V2 T1, and I'm going to divide both sides by V1 so I can solve for T2. Okay. So when I solve for T2, I get 147 Kelvin, and I've got to calculate the decrease in temperature in Celsius. So in order to do that, I would subtract 273. I left that part off there. So I would just subtract 273 from my Kelvin value. So Charles's law is going to look at volume and temperature. Then we get to Gay-Lussac's law. Sometimes this one is also called Amonton's law, but they're both the same thing. They look at the relationship between pressure and temperature, which once again is a direct relationship. And since we're dealing with temperature here, temperature again must be in Kelvin. Pressure doesn't matter, but temperature has to be in Kelvin. So here is an example of a problem involving Gay-Lussac or Amonton's law. If a car tire is filled to a pressure of 32.0 psi at 75 degrees Fahrenheit, what will be the tire pressure if the tires heat up to 120 degrees during driving? So I know I'm dealing with pressure and temperature because those are the variables they give me. And the first thing I've got to do is convert Fahrenheit to Celsius to Kelvin. So I do that. You can see there in my calculations, I take my Fahrenheit, subtract 32 degrees, and then multiply by 5, divide by 9. And I end up with these Kelvin values. And I'm looking for P2 because they wanted to know what the tire pressure would be if the tires heat up to 120 degrees. So when I set up my equation, I am going to set it up so that I'm solving for P2. So you can see here I've cross multiplied P1 times T2 equals P2 times T1. And I divide both sides by T1 so that I can get my P2 by itself, my second pressure. So I multiply and I end up with 34.7 psi. And we look at this and say, well, does this make sense? Well, yes, it makes sense, because I know if temperature increases, pressure should also increase, and my pressure did. It went from 32 to 34.7 psi. I used 3 significant digits because that's what I was given, psi. A lot of times students will be tempted to use the significant digits associated with temperature, but we're going to use the significant digits associated with the other measure, the other variable, which in this case is pressure. So I'll use 3 significant digits. And then our fourth law that compares 2 variables is Avogadro's law. You know, we talked about Avogadro when we were talking about our stoichiometric relationships, that we have, you know, Avogadro's number, which is the number of, you know, atoms in a mole. So we continue this kind of theme as we look at gases, in that we have a direct relationship between the number of moles of a gas and its volume. So you'll see here our equation, V1 over N1 equals V2 over N2, and we're going to let N represent the number of moles. So we have a direct relationship. As we increase the number of moles, we increase the volume. If we decrease the number of moles, then we decrease the volume. Now, this problem is a little bit complicated, but I wanted to show you what all you could do with this type of problem. A cylinder with a movable piston contains 2.00 grams of helium at room temperature. More helium was added, volume was adjusted so that pressure remained the same. How many grams of helium were added to the cylinder if the volume was changed from 2.00 to 2.7? The temperature was held constant. All right. So we started out with 2 grams of helium at room temperature, and the volume was 2.00 liters. And we increased the volume to 2.70 liters, and I want to know how many grams. Well, N is the number of moles. So the first thing that we have to do is convert our 2.00 grams of helium to moles. And I do that using the molar mass. So you can see my calculation there. 2.00 grams, and I set up my conversion factor, and that's going to be times 1 mole over 4.00 grams, and that's going to equal 0.500 moles. So now I have V1 and V2, I have my N1, and I've got to calculate N2. So I set up my equation, and just like the others, I cross multiply so that I don't have all those weird divisors in there. So V1 times N2 is equal to V2 times N1. And I'm going to divide both sides by V1 so I get that N2 by itself. So I get N2 as 0.675 moles. All right. Now, they wanted to know how many grams, so we're not there yet, were added. Not how many we ended up with, but how many were added. So we have to look at how much we just calculated and subtract out what we already started with. So you can see that calculation down here at the bottom. 0.675 moles minus 0.500 moles. So we had 6.675 moles total. But we subtract out what we started with because the problem asks us how many were added, not how many we ended up with. Okay? So we subtract that and get 0.175 moles, and then I use molar mass to convert that to grams, and we have 0.70 grams. And really that should be 0.700 grams. We should have 3 significant digits there. So make sure that you're aware of what the question is asking. And also keep in mind all of these conversions that you've learned throughout this semester, that you need N, which is moles, but you're given grams. You know, don't just throw your hands up and give up. Think about, okay, I have grams. How do I get to moles? And then if they throw this in here, how many grams of helium were added? And that's say, okay, well, they don't want to know how much I ended up with, but once I have that calculated, then I could subtract the amount I started with. Now, we can put all of these together into the ideal gas law, where pressure times volume is equal to number of moles times the ideal gas constant, R, times temperature. Excuse me. This time, though, we get a little more specific with our units. You'll notice pressure has to be in atmospheres, volume in liters, of course, number of moles will be mole, and then temperature has to be in Kelvin. And the reason why we have to use those particular units is because of the units that we see in our ideal gas constant. Okay. So you can see I've got in my ideal gas constant liter times atmosphere divided by mole Kelvin. So in order to be able to cancel out these values, I have to make sure that my pressure is in atmospheres, my volume is in liters, my N, of course, is moles, and my temperature is in Kelvin. So if you start the equation and you don't have these particular units, then you're going to have to convert first. You're going to have to do some conversions in order to get to that particular unit. So let's look at an ideal gas problem. A sample of gas at 25 degrees Celsius has a volume of 11.0 liters and exerts a pressure of 660.0 millimeters of mercury. How many moles of gas are in the sample? So I'm given temperature, I'm given volume, I've been given pressure, and I want to know number of moles. So I have to use the ideal gas law. I don't have any choice because I have all of these variables. So they've given us pressure in millimeters of mercury. So I've got to convert my millimeters of mercury to atmospheres. And I know from the first mini lecture I did here that 1 atmosphere is equal to 760 millimeters of mercury. So I set up my conversion, and my pressure then is 0.868 atmospheres. Volume, they gave it to me in liters. That's what it has to be in. I'm trying to solve for N. I know R, it's the same every time. And then temperature I was given in Celsius, so I add 273 to end up with 298 Kelvin. Now I'm solving for N. In order to get N by itself, I need to divide both sides by RT. So my equation to solve for N is PV divided by RT. And when I plug that in, you'll notice how my units cancel with the units on the ideal gas constant. Atmospheres cancel, liters cancel, Kelvin cancels. I'm left with moles, which is what I'm trying to solve. And when I do the math, I end up with 0.390 moles. I use 3 significant digits because that's how many I have in my problem. So ideal gas laws. A lot of students sometimes will try to use the ideal gas law when they don't need to. So make sure that you're given 3 variables and are looking for the 4th, and they're all different. You know, yeah, you were given 3 variables before, but 2 of them were always the same. In an ideal gas law, you're given 3 variables that are all different, and you're looking for the 4th one. Another gas law that we have is the combined gas law. And what this does is, and we call it the combined gas law because it puts Boyle's law, Strauss's law, and Gay-Lussac or Edmonton's law all together. So this would be used in cases where you're given, 2 pressures, 2 volumes, and 1 temperature. So sometimes students get confused with the combined gas law or the ideal gas law, but remember, ideal gas law also has the number of moles. So if there's nothing in there about the number of moles or the amount or the mass of the gas, then you're pretty safe to assume you're using combined gas law if you're given the other variables. Now, one other thing that we can consider is the relationship between gas densities and their molar mass. And we can derive an equation that allows us to calculate density of gases using pressure, temperature, and molar mass. So if we look at this equation that I have written here, I've just moved the ideal gas equation around, and I've put N over V is equal to P over RT, which if I cross multiplied that, I'd be right back to PV equals nRT. Now remember, density is mass over volume. And with the ideal gas law, we can determine, number of moles over volume. But if we multiply each side by the molar mass, and if you look at that left side of the equation, I have moles times grams per mole at the top. So that's going to cancel out. The moles are. So I'm left with grams per liter, which is density. So density is equal to pressure times molar mass divided by R times temperature. Okay, so I just extrapolated that equation from the ideal gas equation and multiplying both sides there by molar mass. So density is equal to pressure times molar mass divided by R times T. So what does that tell us? Well, that tells us that the density of a gas is dependent upon the pressure, the molar mass, and the temperature. Okay. Now, since pressure and molar mass are at the top, if we have an increase in pressure or molar mass, then that gives us an increase in density. But if we have an increase in temperature, we get a decrease in density. And so to give you kind of a real-world example of this, if we have an equal pressure and molar mass, but a different temperature, the higher temperature is less dense. So hot air rises. Okay, you've always heard that your whole life. Hot air rises, right? Well, this is why. We have an equal pressure, so if we're in a room, the pressure is going to be equal no matter where we are in the room. And we're talking about air, so we have the same molar mass of the air. But if our temperature is different, if we have hot air and cold air, the hot air is going to rise because it is less dense, and it's going to sit on top of the cold air, which falls because it is more dense, because it has a lower temperature. So we can work out an equation that looks something like this. What is the density of carbon tetrachloride vapor, just another word for gas, at 714 torr and 125 degrees Celsius? Now, I made a little note here because I ran out of room on my other slide. Since we derived this equation from the ideal gas equation, P must be in atmospheres and temperature in Kelvin. Okay. We use the ideal gas law to derive this equation, so our units must stay the same that we use in the ideal gas law. So first thing we're going to do is convert torr to atmosphere, and again I'm going to use my conversion factor that 1 atm is equal to, or 1 atmosphere is equal to 760 torr. So that gives me 0.939 atmospheres. Then I have to convert my Celsius to Kelvin. So I take my 125 and I add 273. Now I get 398. Then I have to figure out my molar mass of carbon tetrachloride. Well, I know from my naming rules that carbon tetrachloride would be CCl4. And I get the molar mass of that. My molar mass of carbon is 12.01. My molar mass of chlorine is 35.45, and I have 4 of those. So my molar mass is 153.81 grams per mole. And of course, R is always R. 0.0821 liter times atmosphere divided by mole times Kelvin. So now I plug it in. Pressure times molar mass divided by R times temperature. And you'll notice that everything cancels out except gram and liter. So my unit for density is going to be grams per liter, because density, remember, is mass per volume. So the density of carbon tetrachloride gas at 714 torr and 125 degrees Celsius is 4.42 grams per liter. Don't let these equations scare you, okay? Don't let them scare you. They're not scary equations. You're going to be given in this case, since R is constant, you're going to be given 3 variables, and you just have to solve for the 4th one. So don't let this confuse you. When you see this density of carbon tetrachloride vapor, don't let it confuse you. You know that density is equal to pressure times molar mass divided by R times temperature. Now, if we need to, if we're given density but not molar mass, we can take that same equation, rearrange it to solve for molar mass, and end up with molar mass is equal to density times R times temperature divided by pressure. So here is an example of this. What is the molar mass of an unknown hydrocarbon whose density is measured to be 1.97 grams per liter at STP? So we're given density. We want to know molar mass. You're thinking, wait a minute, STP, I don't know what that is. Well, STP stands for standard temperature and pressure. STP is equal to 273 Kelvin, 1 atmosphere. Okay? So when it says STP, don't freak out like, oh, I don't have temperature, oh, I don't have pressure. You do. 273 Kelvin and 1 atmosphere of pressure. So again, I just plug it in. 197 grams per liter times 0.0821 liter times atmosphere divided by mole Kelvin times 273 Kelvin divided by 1 atmosphere. My molar mass is 44.2 grams per mole. So again, don't freak out when you see this, and don't try to go to the periodic table and like, well, I don't know what my molar mass is because they tell me it's unknown. You can figure it out as long as you have density, temperature, and pressure, which you do. Now we can also use these gas equations to help us complete reaction stoichiometry. So remember a few weeks ago we did stoichiometry where we started with 5 grams of this. How many grams of that would we end up with? Well, we can do the same thing using our gas equations to help us out. So I'm given this equation. 2NaN3 solid decomposes into 2Na solid plus 3N2 gas. This should look familiar to you because this is the equation that takes place in an airbag. So an airbag is a volume of 36 liters. It's going to be filled with nitrogen gas at 1.15 atmosphere and 26 degrees Celsius. How many grams of NaN3 must be decomposed? Okay. So we're given pressure, we're given volume, we're given temperature of nitrogen gas. And we want to know how many grams of sodium nitride has to be decomposed. Okay? So, first thing we've got to do is use our ideal gas equation to determine our number of moles of nitrogen gas, because that's what we're solving for here. Yes, we've got to eventually get to sodium nitride, but for now, okay, we're looking at nitrogen gas. So the first thing we've got to do is figure out our number of moles of nitrogen gas. So I'm going to set up my ideal gas equation so that I can solve for that. And I'm given temperature in Celsius, so I convert that to Kelvin. So you see there, I've got my pressure, volume, R and T, and I'm solving for N. And I get 1.626 moles of N2. Now again, this is N2, okay, nitrogen gas. But I need to know how many grams of sodium nitride. So now I can work my stoichiometric problem. I've got my moles of nitrogen gas. That's something I know how to work with. So I go 1.626 moles of nitrogen gas, and then I use my mole to mole ratio from my balanced chemical equation, and I have 2 moles of sodium nitrite over 3 moles of nitrogen gas. Then I use my molar mass of sodium nitrite, and I end up with 70 grams of sodium nitrite. So this is another one. You look at and you freak out. It's like, oh, I don't even know how to begin. Yes, you do. You know the ideal gas equation. You can calculate your number of moles of nitrogen gas, and then use that along with your balanced chemical equation to get to the proper answer. I'm going to stop there and then pick up with partial pressures and mole fractions and kinetic molecular theory in lecture number 3 for chapter 10.